I would like to begin with an interesting question. Can you name some ways in which the subject of probability theory is different from real analysis? Now, what's the point of this question? Well, think about this. In probability theory, we talk about probability spaces. So we have a sample space, but a sample space, this is just a set. Then we have a collection of events on which we can compute probability, and that's a sigma algebra defined on a set, on the set sigma. And then you have P, and what is P? This is a probability, this is a measure. This is a measure on, well, you can just say it's a measure on this pair. That it evaluates subsets of omega as long as they're coming from that collection. So it's a measure, but it's a measure that has been set to be equal to 1. It's a measure with the property that when you evaluate it on the entirety of the space, it's equal to 1. Then we talk about random variables. What is a random variable? A random variable, we usually call it X. It's a mapping from the sample space to the real line. And we put the condition that we want it to be measurable. Measurable just means that if you pick a Borel set, a subset of the real line that is a Borel set, and you pull it back, you get something in the sigma algebra. So a random variable is, we just call it X, but technically it's just a function. We call it P, but in real analysis notation, this will be denoted by mu for measure. And then we talk about expectation. So when we have a random variable, so if X is a random variable on a sample space, we usually get sloppy. We just write a sample space, but we understand that it comes with all of this data. Then we talk about the expectation of X. But what is the expectation of X? The expectation of X is nothing more than integrating the identity function over, I'm sorry, I take that back, integrating X over the sample space with respect to this probability measure. So it's given by integration. So as you can see, you can replace expectation by an integral. So when you look at this, this is real analysis, this is real analysis, this is real analysis, and it really feels like all we're doing is we're just doing real analysis. How is this really different from probability theory? So this is what makes the question interesting. And as you can see, the foundations of probability theory, at least in the way Kolmogorov set up the foundations of probability theory, is that the foundations are based on real analysis. However, one key distinction, one way in which probability theory is very different from real analysis is, and this is what we'll talk about today, is this idea of independence. And as far as I know, independence is not a concept in real analysis whatsoever. It is something that is truly very special and unique to the subject of probability theory. It's very important, and I think it's so important that it depends a lecture all dedicated to this notion of independence. Those of you who have maybe taken an undergraduate course in probability theory, you've seen independence, and even if you've never even taken a course on probability theory before whatsoever, I'm sure you've heard of the notion of independence, and that's what we'll talk about today. And as is the case, we will define independence in a more sophisticated manner, more so than an undergraduate course. It's going to include what you're familiar with. So if you've seen independence in an undergraduate course, our description of it will be the same thing. It will just use fancier language. It's a little bit reminiscent of the way we define the distribution of a random variable. We define distribution by the push-forward measure. It's a more sophisticated way of saying it, but it does generalize something that you have seen before if you've ever studied undergraduate probability theory. Now, before we get to independence, it will be helpful to first discuss the product of measure spaces. I would like to talk about that first because it's going to come up again anyway, and so it makes sense that we talk about it right now. So here's going to be the setup. Let's remove all of this. So we're going to assume that we have a measure space, and we have another measure space. So we have these are going to be measure spaces. If you forgot what a measure space is, a measure space is just like a probability space, with the only condition that this function mu, so I'm writing mu without a subscript because I'm referring to both of them, it takes events, sometimes they're called measurable sets, but it takes events in the sigma algebra and it maps them, instead of mapping them to the interval from 0 to 1, it maps them to the interval from 0 to infinity, allowing the possibility that something is infinite. This is what happens, for instance, when we talked about the Lebesgue measure. The Lebesgue measure, it possibly assigns infinity to a subset of a real line, to a Borel set. But if you do not like that, you can just assume that these are probability measures. That would be sufficient for what we want. Okay, so this is going to be the setup that we're going to be using. And what we want to do is we're going to construct a measure space on the Cartesian product. Okay, so we're going to take the Cartesian product. The Cartesian product, as you all know, this is simply the set of pairs. So this is going to be, you can say this is the set, let's say x comma y, where x is chosen in omega 1 and y is chosen in omega 2. So that's what we call, let me write that a little bit better, omega 1, omega 2. So that's what we call the Cartesian product. Now, when you're constructing a measure space, you have to start with a set, but then you need the sigma algebra. So what is the sigma algebra? So the sigma algebra on omega 1, omega 2, on this Cartesian product, will be generated by all sets, by all subsets. So a sigma algebra consists of subsets. So it'll be subsets of the Cartesian product of the form, let's say E1 Cartesian product E2, where E1 is in the first sigma algebra and E2 is in the second sigma algebra. Okay, so I want to give a warning here. Warning. So an event of omega 1, omega 2. I realize that I have a tendency, for whatever reason, to keep on saying sigma. So sorry about that. But I'm sure you noticed that, and it's not that serious. An event of omega 1, omega 2 is not necessarily of the form E1 times E2, where E1, E2 are events in omega 1, omega 2. So to show you what I mean by that, by the way, if you're wondering why I put a backslash, this is just a habit, because those of you who are comfortable with LaTeX, if you use LaTeX, this is the way you write omega. So that's just an automatic habit. It probably would have been better not to write it, not that it really matters. So to show you what I mean, if you take the real line with the Borel algebra, so let's say this is omega 1, A1, and then I'm just going to take the same thing again. So this is going to be omega 2, A2. So in this case, these two measure spaces, well, I'm not putting a measure on them yet. I do not really care about that for the moment. But these two measure spaces are going to be the exact same thing. This is just the real line with the Borel algebra. So what we're going to do is we're going to create the plane, so the Cartesian product of the real line with itself, so the plane, and then you're going to have a new, there's going to be a new sigma algebra here, and you have to be careful what it is, you're not just going to take products of a set here with a set there. So since the Borel algebra happens to be generated by intervals, let's just look at intervals. So if I and j are intervals of the real line, then the Cartesian product is a rectangle, right? So if this is r times r, then you have an interval going like this, and then you have an interval going like this, and then they generate for you a rectangle. But so you might think that this new sigma algebra is going to be the sigma algebra that's generated by all, I'm sorry, it's the sigma algebra consisting of rectangles. But the problem is rectangles do not form a sigma algebra. So very easy example, if you just take two rectangles and you take their union, well, you can see that the union is no longer a rectangle. The intersection is a rectangle, but the union is not going to be a rectangle. So rather, that's what we're saying, that the sigma algebra will be generated. It's generated by sets of this form. So in the case of the plane, the two-dimensional plane, it would be generated by the rectangles. It's not necessarily the rectangles themselves. When you allow the possibility of using a countable number of rectangles, you can generate some fairly complicated subsets. So for instance, the disk, the two-dimensional disk, would be in the sigma algebra because you can, of course, as you can see, you can just exhaust the disk by using a countable number of rectangles and fitting them in. And if you unionize them and you take the union of all of them, they will exhaust and they will completely fill out the disk for you. So that's why we're saying that the sigma algebra is not the collection of sets of this form. Rather, it is generated by things of this form. Those of you who might be familiar with topology, it's not a requirement for this course, but if you have ever taken a course in point set topology, you probably recall the product topology on two topological spaces. And the product topology is you sort of start with products of open sets, but that alone is not what gives you the topology. You sort of look at what that thing generates. So it's the same idea over here. So this is just a small warning. Okay, so that's what the sigma algebra is. And I'm going to give the sigma algebra a name. So let's give it a name. Some people like to use the notation. So let us denote this sigma algebra by, so how do you want to call it? Now, you could, if you want to, I have seen some authors call the sigma algebra A1 cross A2. However, this notation is a little bit deceptive because what would this be? This would then be the set, right? It would be the set of pairs x comma y, where x is an A1 and y is an A2. So this would be the collection of pairs of measurable sets, which makes no sense because that's no longer even a subset of the Cartesian product. If you think about it, right? Like if you pick an event, right? If you pick an event and then you pick another event, if you take the pair of, if you form a pair of those two events, that's no longer a subset of omega 1, omega 2. Right? That's not even a subset of that anymore. So that does not even make sense. So you could use that notation if you want to, but the other problem is, remember what we said, the sigma algebra on this product, on this Cartesian product, is generated by sets of that form. So it's better to use a different notation. The notation that I've seen people use is they use the tensor product notation. However, this notation is also not the best notation to use for the following reason. So let's say this, the tensor product usually means something completely different. Maybe there's a way to relate this to the usual tensor product, but then you will get way too far off topic and it's not worth it. The tensor product, it's an idea, it's a very important idea in algebra, especially in commutative algebra. It appears a lot in algebraic geometry. It appears a lot in number theory and so on. Anything that involves heavy algebraic topology would use this. It's very important. It's an idea in algebra. It's a very important idea in algebra. And if you've never seen the tensor product before, do not worry about it. It's not going to come up in this course whatsoever. I'm just giving you a little bit of a warning that if this is your first time seeing this notation, I do not want you to leave this lecture thinking that that's what the tensor product is. This is just notation for the sake of this lecture. Another notation you can use is maybe you can just juxtapose the two algebras together. Whatever, I'm not sure which one to use. I'll use this one. So that's going to be the algebra. And how do we construct a new measure? And now we construct, okay, so so let's write this as a proposition plus definition. You're going to see what I mean. We're going to define something. The definition will be based on the property, and the proposition will just assert that this property exists. So here's how this goes. Let omega 1 A1 mu1 and omega 2 A2 mu2 be two sigma finite measure spaces. Let me use a different color here, sigma finite. Sigma finite is a it's a technicality in real analysis. It just says that it's possible to partition your set into a countable collection. That's what the sigma represents countable, into a countable collection of events. So events here simply refers to subsets coming from the sigma algebra. So you can decompose omega into a countable union of events so that each event has finite measure. So the go-to example is the real line with the Lebesgue measure. So the Lebesgue measure of the real line is infinite because the real line is an interval, and it's an interval of infinite length. So its Lebesgue measure is going to be infinite. However, you can decompose the real line in the following way. You can take, so here's one way to do it. You take the numbers from 0 to 1, then you take union from 1 to 2, union from 2 to 3, and so on in both directions. This is a countable union, and each of these subsets are intervals, so they belong to the Borel algebra, and the Lebesgue measure on each of these is equal to 1. So they all happen to be finite. So that's what it means to be sigma finite. Sigma finite comes up a lot when you're talking about integration. When you want to integrate something, you want it to be sigma finite because then you want to be able to break up your space into a countable number of subsets, so then you can form a series out of them to form like an approximating Riemann sum for the interval. So it's a technicality in the subject that comes up. So that's what it means to be sigma finite. If, by the way, if this happens to be a probability space, then it's automatically sigma finite because the probability measure on the entire space is already finite. It's already equal to 1. So then you automatically have that without any problems. So in the case of probability theory, which is what we're interested in, this is not even an assumption. It's not even going to come up. So then here's, there exists a unique measure. There exists a unique measure on this pair. So on the Cartesian product with this sigma algebra that's formed when you generate it by all of the products of all of these events. So this is going to be the sigma algebra we're going to be using. So there's a unique measure on this with the property. So there's a unique measure. So how do you want to call this measure? So this is a question of notation. How do you want to call it? So I've seen some people call this measure mu1 tensor mu2. Again, not the normal notation for the tensor product, but that's the notation we're going to use. So this is when you put the two measures together. You're using sort of these two measures to construct a new measure. So this is going to be what we'll call this new measure. So this is going to be a measure on this pair with the property that if you apply it to, so if you were to take it, so again, the sigma algebra is generated by sets of this form. So if you take one of these rectangles, okay, let's call them rectangles. So if you were to take one of those rectangles and you were to evaluate it using this new measure on this Cartesian product, the way it will calculate is it would be equal to, it will have the following property, that it's mu1 of E1 multiplied by mu2 for E2, and this is for all E1 in A1 and E2 in A2. And there's a convention here. With the convention, by the way, this convention is not going to come up in probability theory, but in general in measure theory, with the convention that 0 times infinity is to be interpreted as 0. Because after all, you need to understand, it is conceivable that maybe this is equal to 0, and it's conceivable that this is equal to infinity. If this was like the number 2 and this was infinity, then the reasonable way to interpret that should be infinite, of course. But how would you... So if this is, I mean, it's because these are measures, this number is at the very minimum 0, and at the very maximum it could be positive infinity. So you need a convention of what happens with this indeterminate form, and the convention here is that it would be interpreted always as 0. Okay, so what's the definition? So the definition is we call this triple omega 1 Cartesian product omega 2 script A1 tensor script A2 comma mu1 tensor mu2 as the product measure. So we call it the product measure. So that's the definition. So the definition, so we're defining the product measure. The proposition asserts that there exists a measure on this that has that property. How do you prove it? We're not going to prove it because this is really a real analysis type of a course that would be appropriate for a course like that. But basically, it feels a little bit like the Carathéodory extension theorem, that you first define a measure on easy to understand subsets, and then you want to be able to extend that measure on a sigma algebra. That's kind of how it feels a little bit. Yeah, so it's not particularly difficult. It just takes effort to go through and prove it. This is something that will definitely be proven in a real analysis book. I do not want to go in there. I think it's fairly believable that you can do this. You can, of course, look at the Wikipedia page. So as you can see, it says it's similar to the product topology of two topological spaces. But if you do not know that, it does not matter. It says, so if you have, so as you can see here, you have two measurable spaces. So you're not even saying what the measure is yet. You generate, right? So it's generated by subsets of this form. They call it the tensor product sigma algebra. That's the notation that they use. And a product measure, and they say it's also denoted by this. So it is defined to be a measure on the measure space that it satisfies this. And as they say, if you're multiplying and one of them is infinite, we define the product to be 0. The existence of this measure is guaranteed by the Hahn-Kolmogorov theorem, which, as it says, as you can see the pop-up that comes up. Well, I'm not sure if you can see the pop-up come up, but if you click on it, it's also the Carathéodory extension theorem. The uniqueness is guaranteed only in the case where these are sigma finite. You can look it up what it means to be sigma finite. So there's actually a lot of information here. So you can find the information on Wikipedia if you're interested. You'd not even have to resort a book, but you can look up maybe the proof of that in the book if you really care. Not very interesting, but I want to just state what it is so then we know what we mean when we talk about the product measure. Now, returning back to the example of the real line. So as we know, on the real line, we have the Borel algebra and we have the Lebesgue measure. So let's use 2 copies of this. So in this case, these are going to be the exact same measure space. So then we can talk about the product measure space. So it's going to be R2, the plane, and then it would be the Borel algebra tensor, the Borel algebra, which maybe we can denote it as like this. So power to the 2, maybe you kind of use tensor product. I mean, maybe you can write b squared if you understand what that means, but whatever. I'll write it using tensor notation. And then you would have lambda, tensor lambda. Maybe you write it lambda squared. Maybe you write lambda tensor 2, whatever you want to write it. So that's what it would be. Now, what is this supposed to represent? So intuitively, lambda, this is length. Length is a one-dimensional measure. You're measuring something in dimension 1. Because after all, how is the Lebesgue measure defined? You start with an interval, and the Lebesgue measure of an interval is just the length of the interval. But then we take this notion of length and we generalize it to a larger class of subsets. So like, for example, we can talk about the Lebesgue measure of the rational numbers. So we're basically asking, what is the length of the rational numbers? In some sense, it does not really make sense because the rational numbers are not an interval anymore, but that's the whole point, that we're trying to generalize length to a larger collection of subsets. This is going to be two-dimensional measure. This is the measure on the plane. So lambda squared, this is supposed to really represent area, and this is now two-dimensional measure. And the idea here is, of course, is that if you have the two-dimensional Lebesgue measure on a rectangle, right, on a rectangle, how do you find it? Well, a two-dimensional Lebesgue measure on the rectangle, you would look at so this is a product of two intervals, and you would take the one-dimensional measure of this length, whatever that is, and then you would multiply it by the Lebesgue measure of the other length, of the other side. Right, this is sort of like, this is like E1 Cartesian product E2. So this is going to be E1 and E2. You're just multiplying the Lebesgue measure of the two intervals that go into it, but really all you're doing is you're finding the area of the rectangle that it forms. Now, if you have a more complicated type of a set, let's say a disk, and you want to find the Lebesgue measure of a disk, well, how do you typically think of an area of a disk? Like, how do you typically think about it? Well, because it is a measure, it is countably additive on disjoint subsets. And so what you would do is you would cut it up into rectangles that are non-overlapping rectangles, and you have to use a countable number of them because a finite number of rectangles will never perfectly fit into a disk. But you kind of do that, and as you do that process, you would then say it is the sum, right? It's the sum of the areas. It's the sum of the areas of the rectangles that make it up. So because of this, lambda squared plays the role of area. It's, in some sense, it's an area function. It's a function that evaluates areas on the subsets. Now, because of pathological reasons, as we have said, it's generally not possible to talk about area of an arbitrary subset of the plane, right? There's no way to define a measure function on every subset. That was sort of the example we had before. Strange things begin to happen. So that's the reason why we restrict it to a collection of subsets that at least form a sigma algebra, which is generally good enough for the purposes of doing analysis, because then you can work with infinite sequences, but it's not too big enough that it leads to these strange results. So, but that's the basic idea, that these are like the collection of events on which area is a defined notion, and then this is supposed to represent area. And then you can, of course, go beyond that. You can take, if you can do it with 2, you can do it with 3, and then you can talk about R3, then you can talk about the Borel algebra generated by all cubes in 3-dimensional space, and then you would have 3-dimensional Lebesgue measure that's going to play the role of volume. This will now play the role of volume. This also explains the reason why we use the convention that 0 times infinity should be interpreted as 0. To use a very simple example, let's say we want to find the 2-dimensional Lebesgue measure of the singleton set 0 multiplied by the real line. Now, as a picture, this is your 2-dimensional plane R2. The first coordinate is equal to 0, so the x-coordinate, as you would call, that's equal to 0, and the y-coordinate, it could be anything. And so that will be a subset that looks like this. Right? That's what it would be. So using your intuition, you're asking what is the area of this. But what is this? This is a line segment. This is a line segment. This is something that's one-dimensional. And the area of a line segment, it should be equal to 0, right? It should be equal to 0. But because this is a rectangle, it's a product of two intervals, it is equal to the one-dimensional Lebesgue measure of 0 times the one-dimensional Lebesgue measure of the real line. So it's going to be equal to 0 multiplied by infinity. And the convention here is to set that equal to 0. Okay, so that is what's happening here. I would like to mention Fubini's theorem. I do not think we're actually going to need it, but because we are talking about product measures, it makes sense to mention it. It also is going to show you something interesting about integration theory. Let's go back to the Wikipedia page again. And if you scroll down so I should have showed this earlier, that on the page for the product measure, there is Fubini's theorem. And Fubini's theorem is the way you integrate a function in the product. So the way that it goes is x and y are sigma finite measure spaces, and you give their product the product measure, and it says it is unique under these assumptions. So Fubini's theorem says that if you have an integrable function on the product, so what does it mean to be integrable? So they say it means the function is measurable. Measurable just means you pull back. So f is a function, so it maps the product to the real line. And measurable just means it's like a random variable, that if you take a Borel set and you pull it back, then you get an event in the product. And to be integrable means that the integral exists as a finite number in the absolute sense, that the function in absolute value, it integrates to something that's finite. So under these assumptions, Fubini's theorem says that if you want to calculate the integral, you integrate one variable at a time. You do what is known as an iterated integral. So basically what it's saying is you want to integrate, I'm going to use slightly different notation. So let's say you want to integrate a function f on the product, and you want to integrate this with respect to the product measure. So assuming that this function is integrable, and there are theorems in analysis that will tell you if a function is integrable. So one way a function would automatically be integrable is if it happens to be a bounded function, and these are probability spaces. So if it's a non-negative bounded function, then you would have that. But there's other theorems as well. If it's a continuous function, but if you're talking about continuity, then you need some extra structure to make sense of continuity. But I'm basically saying there are conditions that will tell you if you know if something is integrable. But if it happens to be integrable, here's the way you can do it. You can say that this is the same thing as integrating over omega 1. It does not matter in what order you do it. It's the same thing as integrating omega 1 g d omega 1, where g is the iterated integral. So basically what it is, g is a function on the first factor. So this is going to be a function on the first factor, and it's defined by the rule that g of x is equal to, you integrate over omega 2 f, you set the first variable to be equal to x. Okay, so f is a function, right? So you have to kind of understand that f is a function on the product. It's a real valued function on the product. And so if you set the first variable, if you pick a certain value for x, right? So that's kind of what I mean by the dot. This is sort of the variable that is free, and this is the one that's being set to a particular number. Then this is now a function of the remaining variable, which is on omega 2. So this is what we mean by G. You integrate out the first variable. I'm sorry, you integrate out the second variable. So if you fix the first variable and you integrate out the second variable, you're left with something, right? Something that depends on the first variable, and whatever function that is, you call that G. And if you integrate that again with respect to the first measure, then that will give you the value of the function integrated on the product. So this is called Fubini's theorem. Now, what's interesting is, and I'm not sure if we're going to use this theorem, but I just want to mention something interesting, that this theorem is not true in classical theory of integration. There's actually an example, you can find this. So this is example in Spivak, Calculus on Manifolds. And this is the section called Fubini's theorem in that book. And Spivak gives an example that if you wanted to integrate a function, so you're integrating over the unit square, that's not the same thing as integrating f. So you kind of write it like this, f of xy with respect to the first variable, and then you integrate from 0, 1 with respect to the second variable. Something very unusual happens, and the unusual thing that happens is that this does not even exist as an integral. And his example is not even that ridiculous. I mean, it is a slightly pathological example, but the function that he uses is actually fairly nicely behaved. His function is, it's a bounded function. It's a non-negative bounded function between 0 and 1. So you do not have any of that nonsense about things blowing up to infinity. So it kind of goes to show why there's a modern theory of integration. So the classical theory of integration is what we call the Riemann theory of integration, where the way you define an integral over an interval or over a rectangle is by partitioning that interval or that rectangle into subintervals or subrectangles, and then using that to compute what the integral is. Now, in practical terms, most functions in practice, the kind of functions that you do concrete examples with, can be perfectly handled using the classical theory of integration. But nowadays, we use the modern theory of integration for measure spaces. So we can talk about integration in more abstract spaces, which we call measure spaces. And anytime you have a measure space, you can introduce a theory of integration. It is an improvement on the classical theory for all sorts of reasons, not just because it allows you to do it more generally, but this would be one of those instances that the classical theory of integration does not really behave well under these circumstances. So one of the people who pushed the modern theory of integration was Lebesgue. Now, the way he did it was not the way we do it today, but it sort of led up to it, and the way we present it nowadays is the much more sophisticated, improved version. And under this version, you have this Fubini theorem that works out nicely in the end, whereas in classical integration, you're not going to have this. You will need to put the assumption that the function is continuous to know that you can do something like that. But by assuming the function is continuous, you're now automatically putting extra assumptions on the function. It's not as general as you would like it to be. So I'm just mentioning it just for maybe people who are interested. Maybe you've wondered, like, why do we need this improved theory of integration? Why not just use the classical Riemann theory of integration? They often tell you because there are functions that Riemann integration cannot handle. And that is true, but that's not a very good answer because most of those functions are very pathological. I think a much better answer is that you do not have theorems like this. Theorems that you would like to be true are not really true. And when you're proving theorems in general, you do not really know that much about the functions. After all, it is a theorem. It's a fairly general theorem. You do not know that much about the function, and you would like to be able to do things like that. And with the classical theory of integration, you have limitations on the kind of things you can do. And there's other drawbacks So the answer that they give you that, oh, it's because there's functions you cannot integrate, that's not a very good answer, because there's functions you cannot necessarily integrate even using the modern theory of integration, but we do not really care about them. It has more to do with the properties that integration has that it does not the properties you want it to have that it does not necessarily have. So I think that's just like an interesting comment about that. But I'm not sure if we're going to use this Fubini's theorem. It might come up. Also, I want to finish with one more thing. This is completely off topic. But some of you who, if you're familiar with category theory, maybe you might be interested in this question. You might ask, is the product measure a categorical product? This is something you can ask. You can ask, is there such a thing as the category of measure spaces? It's actually a somewhat technical question. So there's a category, so there's something called measurable spaces, which is a set with a sigma algebra, and then there's something called measure spaces, where you have a set with a sigma algebra and with a measure, and you have a categorical product for one, but not a categorical product for the other. If you're interested, I would just recommend, it's completely unnecessary for us. I just imagine that we have a large variety of audience watching these lectures. Maybe some of you know what that is. Maybe you're interested. You can kind of search for it on Math Overflow. They actually discuss that. If you search for something like product measure, categorical product, you'll see an interesting response to that. It's not that simple, but I'm just mentioning it for maybe some of you are wondering about that. That's like an interesting thing to think about. But now we want to return back to probability theory. Now we're going to talk about what are known as higher dimensional random variables. At the moment, you might be confused and you might say, what does this have to do with what we're doing? Because we're ultimately trying to get to this idea of what it means to be independent in probability theory. But I find it helpful to first talk about this first, because then once we're familiar with this idea, it would be a lot easier to then go ahead and define independence. Now, these are also called, so these are higher dimensional random variables. We're going to do this in dimension 2, because once you understand how it works in dimension 2, it becomes very easy to generalize this to any dimension. These are called random variables. Some people might call them random vectors. That's another terminology that people use, random vectors. So let's say what that is. So here's a definition. We say x. So this is going to be a function. So what is a random variable? A random variable is a mapping from the sample space. And here we're going to use this sloppy convention that we simply write down the sample space, and we never even bother to mention anything about the measure or the sigma algebra. We understand that's always that's always included in probability theory. So when we talk about random variables, these are functions from the sample space into the real line. But if it's a two-dimensional random variable, then you're just mapping it into R2. That's it. And in general, it would be Rn. You can also call this a random vector, because a point in R2 is sometimes called a vector. So if you have a pair 1, 2, let's say, you can call that a point if you want to think of it as a dot, or you call it a vector if you want to think of it as some kind of arrow or whatever. It's just terminology. They mean the same thing. So you can call it a random variable, random vector, whatever you want to. You can call it like a random point in the plane, whatever you want to call it. But this random vector, two-dimensional random vector, it's a mapping from the sample space into R2. We say that this is a two-dimensional random vector or variable, same thing. If and only if, it's the same idea. If you pull back a measurable set, if and only if x inverse of a Borel set is an event. So when I say an event, I mean it's an element of the sigma algebra, but the thing is, I never mentioned the sigma algebra, so maybe I should just say it like this. And what is E? Where E is a Borel set, in R2. So you have to understand that we have the one-dimensional Borel algebra, which we just call script B. And if we write, let's say, script B tensor 2, or let's say we write it like this, script B tensor script B, so this is the sigma algebra generated by intervals, and this is the sigma algebra that's generated by rectangles. So you would just take an interval on the real line, you take an interval on the real line. If you take their Cartesian product, they form a rectangle in the plane, in the two-dimensional plane, and then the sigma algebra that is generated by all of these rectangles is what you call the two-dimensional Borel algebra. But we just say it's a Borel set in R2, and it's understood from context that we're not talking about a Borel set on the real line, but what we really mean is a Borel set in the plane. So it's the same exact definition as we have before. And just like before, we also have a notion of a distribution. The distribution, so maybe I should have put this in quotations because we're defining what a random vector is. And you can easily generalize this to an n-dimensional random vector where this would just be a Borel set in Rn. And you can figure out what that means. The distribution of x, so let's indicate that x is a random vector, two-dimensional random vector. And how do we get the distribution? Well, the distribution is the push-forward measure. It is a probability measure on the codomain, in other words, so this is going to be a probability measure on the two-dimensional plane with the two-dimensional Borel algebra. So this is going to be a probability measure on that space defined. So a probability measure, we can denote it as P subscript x. So this is the probability measure induced by this random vector. And it's going to be defined by the rule that Px acting on a Borel set, so this is now a Borel set in here, is you would just take the probability measure applied to the inverse image, where this P, if you're wondering what this P is, this is just a probability measure defined on the sigma algebra for this sample space. We're just being sloppy. We're not writing it out like fully, but we understand that it's always there hidden in the background. So that's what we call the distribution of a random vector. So you need to understand that the distribution of a one-dimensional random variable, the way we have been talking, would be a probability measure on the real line. When you have a random vector, the distribution is going to be a probability measure on the appropriate Euclidean space. In this case, we're talking about 2 dimensions, so this would be a probability measure on R2. And it, of course, very naturally generalizes to higher dimensions. Now, just like before, we can talk about things being discrete and continuous. So we say that this random vector that goes into R2 is discrete. I should say this again. It is very common in probability theory to study random variables or random vectors more generally to be one of two types, the discrete types and the other ones which we call the absolutely continuous types. That does not mean that every random vector is necessarily one of those two types. It could be a mixture, it could be something else. It's not that simple, but just in practice that these are the ones that we typically deal with. So we would say that a random vector is discrete if and only if its distribution is a discrete probability measure on the two-dimensional Borel algebra. And what does that mean? That means, so to be discrete, it means it is a sum of point masses. It means that we can express this probability measure as a sum over I, AI, and this is the Dirac deltas PI, where AI are positive numbers with the sum of the coefficients adding up to 1, and Pi are points chosen in the Euclidean plane. So this is the Dirac measure. I'm not going to define what that means. Again, we're not really going to need it in this lecture, but maybe you can go back to the previous lectures if you just want to have a quick reminder about what that means. It's a sum of point masses. The indexing set over here, it is assumed to either be finite, it's a finite set, it's a finite sum of point masses, or maybe a countable sum of point masses, because otherwise this would not make sense if this was uncountable. So you either interpret this as a finite sum of positive numbers or an infinite series of positive numbers. So that's what that would mean. Of course, we can assume they're positive, because if any of them are 0, you would just drop them out and you're left with the only positive coefficients. So that's what it would mean for it to be discrete. And the other one that often happens is when it's absolutely continuous. So we say that x from the sample space into R2 is absolutely continuous. I want to remind you that continuous in general means something else, which we never defined. We never defined what it means for a random variable to be continuous in general, and I do not want to, because we do not need to, so why bother even go there? Is absolutely continuous if and only if Px, the distribution, has a probability density function. And this is going to be a two-dimensional probability density function, as opposed to a one-dimensional probability density function. If you're not sure what that means, so that just means, i.e., that if you take the derivative of Px with respect, now usually we talk about with respect to the Lebesgue measure, but this is technically the two-dimensional Lebesgue measure. In other words, this is the Lebesgue measure that calculates areas of Borel sets in the plane as opposed to lengths on the real line. That the Radon-Nikodym derivative exists with respect to that measure, that this exists. And if you're confused by what that means, it means, i.e., there is a function, let's say f, from R2 into R. So notice that because we're talking about two-dimensional random vectors, this is a function that's no longer defined on the real line. It's now defined on the real plane. There is a function with the property that f is non-negative and that it calculates for you the probability measure by integration. So the probability of the random vector landing inside this Borel set can be calculated by integrating over this Borel set f d. I mean, the notation looks kind of ridiculous, but like you can say maybe equal to, in more classical notation, maybe you're used to, you would write like a double integral, because after all, this is a function defined in the plane, so you would probably use two integrals. This is the way they would write it in like a calculus class. It's just that the further you go into math, the simpler your notation becomes. So a mathematician will never write two integrals, even though technically you are integrating a two-dimensional region. So you would write two integrals, then you would write you're integrating over E, and then you would write f. This is a function of two variables now. So what do you want to call those variables? Maybe we do not want to call them x and y, because that might be confused, but maybe we can call it like u and v or something like that, u comma v, and then we would write, and this is, we're integrating this in the usual sense, because this is, I guess, in like a calculus 3 class, you write like dA or something. That's the way they write it, like dA. This indicates that this is with respect to like the area element, which is exactly what the two-dimensional Lebesgue measure means. But you would write it like maybe du, dv, something, or d. It does not. It's just like in the end, whatever you put there, it's just notation. Like it's not that serious, but that's the way you would write it, right? So you can calculate the probability of an event using this distribution by just integrating a function in the usual sense. So such a function is called the probability density function for your random vector. Okay, so this is the setup for all of this. By the way, this implies, maybe I should say it over here, note, this implies, of course, that when you integrate over R2, f. So if you integrate this function, it has to be equal to 1. The reason for this, of course, is because if you take the Borel set, this is the Borel set in R2, not on the real line, but we can understand from context which one we're referring to. If you were to integrate all of R2, because this is a probability measure, it has to be equal to 1. So whatever that function is, it has to integrate to 1. So this is the idea. This is a generalization of what a random vector of a random variable. This is a higher dimensional random variable. And you can talk about random variables in R3 and so on. You can generalize this. You can even, if you want to go even beyond that, you could maybe replace this by something that's even more abstract than the Euclidean space, but we really do not want to go there. Let's not even bother to go there. And of course, as I've said, discrete and absolutely continuous are not the only two things that can happen when you have a random vector. It's more complicated than that, but it's just that in practice, this is generally what happens. So with all of that said, we can now discuss independence. We now have the tools to define what it means to be independent, specifically what it means for random variables to be independent. I would like to begin with a motivating example, which is very simple to understand, but it will motivate the definitions that are to follow. I do not want to just show you the definitions. I want to lead you to the definitions so we appreciate them more. Let's consider the following game. So we're going to have a game here, and the game is a woman shoots a basketball, and she has a 20% chance to score points, right? To score a point. So I'm sure you all know what basketball is. In this example, you really do not need to know anything about basketball other than the fact that there's this hoop, and you have a person, and the person throws a ball, and you try to make it go through that hoop. The further you are away, the more difficult it becomes. And in the game of basketball, there's what they call the three-point line. If you stay inside, you get 2 points for the shot. And if you stay outside, then you get 3 points for the shot. So we're going to assume that they shoot from what you call the free. Okay, I should actually write it out, otherwise it's going to be confusing. The free throw line. That is, you have your basketball hoop, and then there's a line over here. In the game of basketball, if someone commits a foul against you, sometimes you get to take a free shot. I have to actually write it out because it sounds like the word three, and it might sound like you're shooting from further away. No, you're shooting from the line. So she is shooting from the line, and she has a 20% chance of making a successful shot. And then afterwards, a man shoots and has a 30% chance to score a point. Now, what we're trying to get to is we want to say the man's score is independent of the woman's score. That's what we want to say. Because she can either make the shot or not, but why would it in any way influence what the man is doing? It's not going to influence anything. He's going to take the shot like he always takes the shot. It has nothing to do with what she does. So this is a very simple game. And you have, we can call this like game one. And then you have game two. And in game two, woman is going to shoot, just like before. Then the man, so then the man shoots if the woman misses. And if she makes the shot, if she hits, then he shoots from a further distance, and he has a 10% chance of scoring the shot. So basically, in game 2, you have that basketball hoop, and the woman takes the shot. If she misses, then the man shoots from the same line, and he has a 30% chance to make it. And then they decide to make the game more fair. If she manages to score a point, then the man, instead of duplicating the same shot, will then have to go further back and then shoot from here. But here, he only has a 10% chance of being successful. So this is an alternation to this game. And here we would say the man's score depends on the woman's score. So if she scored 0, then his chances of scoring will be at 30%. And if she successfully scores the shot, the basketball shot, then his chances dropped 10%. So you can see the amount of points that he gets now depends on what she does. So in this case, this is the idea of dependence, and this is the idea of independence. So intuitively, it makes sense. But how do you make this mathematically precise? So here's how you do this. Here's how we can describe it using a sample space. So omega 1, this will represent what the woman does. So she goes first, so that's why we call this omega 1. So omega 1 has 2 possible outcomes, 0 or 1. So she scores 0 points or she scores 1 point. So we're assuming that, unlike basketball rules where you have 2 points or 3 points, here everything is just 1 point to keep it simple. So she can score 0 points or 1 point. However, in this sample space, these are not equally likely to happen. So she would get 1.2% of the time, not percent, but 0.2, and she would get 0 with 0.8. So the probability measure, the sigma algebra here, this is just a power set. These are all subsets. Which is what almost always happens when you have a finite sample space. The sigma algebra is just a power set. It just consists of everything. And the probability measure, so what's the probability measure? Well, the probability measure of an event, well, if you have an event, I mean, it's a subset of that, and there's not that many possibilities, but basically you count this one. Well, I'm not even going to write it out. Like, maybe I'll just show you what I mean. Like the numbers tell you how to do it. But let's say you want to find the probability of the singleton, that would be 0.8. If you want to find the probability of that singleton, that would be 0.2. If you want to find the probability of 0, 1, you just add them together. So it's 0.8 plus 0.2, which is 1. Okay, that would be the probability measure here. And then you have the man. And for him, he has 2 outcomes, 0 or 1. So the sample space is the same. The sigma algebra is the same. But these 2 random experiments are actually not the same because there's a different probability measure. So here you have 0.7 attached to that number, and for this number you have 0.3 attached to that number. And then you have the sigma algebra is every subset, and then you have P2, which I'm not even going to bother to write out what that is. The numbers tell you how to do it. So what happens when they play the game together? So this is where product measures will come in. In game number 1, you have independence. So in game number 1, they both play together. So to correctly describe what takes place, you would say, you would take the Cartesian product of these 2. So you would have 0, 0. So this is the possibility where both the man and the woman scored 0 points. Then the woman scored a point and the man did not. The woman did not score any points. The man scored 1, and then they both scored 1 point. So there are 4 possible outcomes. Now, the idea is that whether or not the man scores a point is independent of what the woman does. So let's think about what the correct number we have to attach to this one. We're saying that, so how frequently does this happen? Well, the woman scores a point 20% of the time. Okay, so 20% of the time, she is going to score a point. But then the man scores a point 30% of the time. So he's going to score, so for him to also get a point, it should be 30% of whatever that is. So you would have to take 30% of that. So it would take 30% of 20%, which is going to be 6%. So the correct number to assign here would be 0.6. And now that you see it, you basically just multiply the numbers together. So this one would be 0.8, 0.7. So this would be 0.56. This one would be 0.2, 0.7. So that would be 0.14. And then this one would be 0.24. And you can check to see that the numbers add up to 1. This is 0.3. This is 0.7. So the numbers do add up to 1, which they should. And the probability measure here, and then you observe that the probability measure on this new sample space, on the sample space of what happens when they play together, is the product measure. It would be P1 tensor P2. Why? Well, just to illustrate, how do you calculate the product measure of, so let's say we apply that to one of the points. Let's say the point is 1, 0. Well, technically it has to be a singleton, so you would say it's P1 tensor P2 applied to, you can write that as the singleton 1 times singleton 0, like that. And then the way the product measure is defined on rectangles, so this is like a rectangle in an abstract sense because it's a product of two things. But the way the product measure is defined on rectangles is you apply the first one to the first rectangle, to the first interval, or whatever you want to call it. I know it's not an interval here, but that's just the analogy. And then you multiply it by the other measure applied to the other, like base times height times the other one. And if you work this out, P1 of 1, well, it's whatever we said over here, 0.2, and this one is 0.7, and that's exactly how you end up getting that number over there. So what you can see is that the probability measure that you end up placing on this new sample space of when they play together is exactly the product measure. Okay, so the basic idea here is this. So basically, what we're saying is the new sample, so the sample space that describes, maybe I should say the probability space that describes them playing together is you take the sample space that describes her game, and then you take the product with the sample space that describes his game. And that's how you end up generating, right? This is the product of two probability spaces, and this is how you end up generating there's this new sigma algebra, which in this case is the power set, and you get the product measure, which is the correct one to use to get the correct probabilities, which capture the idea that the points that they score occur independently of each other. Now, I'm not going to go through the calculation all over again. You can do this yourself. But if you go back to the second game, which is the game in which the score of what the man gets depends on what the woman is, you will see that the way you assign the correct probabilities on the sample points is not given by the product measure anymore, because it's not, that's the whole point. It's not independent anymore. So that's not the way to do that. Okay, so with that, we can now motivate the definition of what it means for two random variables to be independent. So let's make this a definition. Let x and y be two random variables on a sample space. Of course, on a sample space with a sigma algebra with a probability measure, but we often do not reference that. So x comma y are functions from the sample space to the real line, and they happen to be measurable, which just means a Borel set on the real line gets pulled back to something, to an event in the sample space. We say, okay, maybe we should say this, the joint random vector is the vector that you get when you put them together. So if you put them together, then they're going to create for you a random point in R2. So think about this. If you pick a sample point and you apply x to the sample point, you get a real number. Then you take the very same sample point and you apply y to that very same sample point. You get another number. So the pair x comma y, when you evaluate it at a sample point, will produce for you a vector, a two-dimensional vector, right? It has two components. It will produce for you a two-dimensional vector. And this is a random vector. Now, technically, it has to be proven that this is a random vector. You have to prove that a Borel set in R2 pulls back to a Borel set over there, but we're not even going to bother to prove that. That's closer to real analysis than it is probability theory. So we're just going to accept that. So we have a random vector. We call this the joint random vector for reasons that should make sense, because we're joining them together into a vector, right? This is sort of what happens jointly together. So that's the joint random vector. And we say that x comma y are independent random variables if and only if, and like I said, the definition that I'm showing you is the most sophisticated definition of independent random variables. In an undergraduate course, you probably define it differently. Though the idea remains the same, you're not using the fancy language of measure theory to do that, but really you're doing the same thing. We're just doing it in the most general possible way. So we say that x and y are independent random variables. So the idea is, I'm going to show you examples, of course, afterwards to illustrate the idea, but we would say that x and y are independent random variables. Well, you see, the nice thing about our definition is that, like in undergraduate probability theory, what they do is they spend time talking about discrete random variables, then they spend time talking about continuous random variables, technically random variables that are absolutely continuous, they should say. And then they kind of, the two methodologies are sort of similar, but we're doing it in a much more elegant way where we handle everything simultaneously all at once using the nicest definition, where we do not put them into these arbitrary categories of discrete, absolutely continuous, or anything like that. This will work in any circumstance. But we would say that x and y are independent random variables if and only if, so I'll write it down and then we can explain it afterwards, if and only if p xy is equal to px tensor py. So what do we mean by that? Well, let's understand that this is the distribution of x, and this one is the distribution of y. What is it in a distribution? So this is, so both of these, so these individually are probability measures on the one-dimensional Borel algebra. That's what these are individually. Now, this piece over here, as we've said, this is a random vector. This is a two-dimensional random vector, as you can see right over here. So the distribution, this is a distribution that you get from this random vector. So this whole thing taken together, this is the distribution of the random vector. And so it is a probability measure on not the one-dimensional Borel algebra, but on the two-dimensional Borel algebra. And so you're saying that if you were to take this probability measure and that probability measure, which are, so this is a probability measure on this is a probability measure on this, and you then take the product of two probability spaces. So basically, what we're saying is, we're saying that you take R script B Px, and then you take the product with R B Py, that this is the product of two probability spaces, and you're going to get R2, the two-dimensional Borel algebra, and you get a probability measure on that, and the probability measure on that is the one that you get from the that arises from the random vector. So it's the same exact idea, that it is just like the example that we did with the basketball game that was very simplistic, but it's the same idea, that the distribution that you get on R2 is just coming from X and Y, and they're being multiplied together to indicate the fact that they're both happening independently of each other. So that is the sophisticated way of how we define what it means for two random variables to be independent. Later on, we'll talk about what it means for three or more random variables to be independent. But for now, we're just doing it for two. That if you could understand it for two, it becomes easier to understand it for a larger collection. So that's the definition. I want to show you some examples. But before I show you some examples, I first want to state a bunch of propositions, maybe just two propositions first, which are very similar to each other. And then I'll go on and show you some examples of this. Proposition. Suppose X and Y are random variables, are independent random variables. And we're going to have two parts to this proposition, depending on whether or not these random variables are discrete or absolutely continuous. Because, as we've said before, these are the two very common instances of random variables in practice. The first part of the proposition would say that if X and Y are discrete, so that would mean that the distribution, so the distribution is the probability measure that you get on the real line. So if the probability distribution is a sum of Dirac deltas, this indexing set is either a finite set or it's a countable set. The coefficients are positive real numbers that add up to 1, and the pi these are just points on the real line. I'm just too lazy to write all of that out. So this is the distribution of x, and the distribution of y is also a sum of Dirac deltas. It's a sum of point masses. Bj delta qj. So it is conceivable, for example, that this is an infinite set, countably infinite, whereas this is a finite set. In this case, we're assuming that x and y happen to be discrete. Then the random vector the random two-dimensional, maybe I should say it like this, the two-dimensional random vector. So the random vector, what you get when you joint them together. So this is the joint random vector. So this is now a mapping from the sample space to the real plane, is also discrete, and its distribution will now be a probability distribution no longer on the real line, but rather a distribution on the real plane. It's going to be a sum of point masses, and you can maybe guess how this is going to go. So this would be a sum where you multiply the coefficients. Notice that this is still a countable set. Well, if I and j are countably infinite, then the indexing here is still going to be countably infinite, because the coefficients are really indexed by the Cartesian product. And the Cartesian product of two countable sets is countable. So you can write it like this, and then say I comma j belongs to the Cartesian product. So it's the product of those coefficients and then it would be multiplied. It would be a sum of Dirac deltas, and then the points would be pi comma qj. So that is what we get. And I'm going to leave this as a homework problem. You can prove this yourself. It's not difficult. And instead, what I'm going to do is I'm going to write down a very similar result in the case where the random variables are absolutely continuous. And then we're going to say something very similar about the random vector that you get when you join them together. So the other version of this that comes up a lot in the subject is that if x and y are absolutely continuous random variables, and so it means that the distribution can be determined by integration. So it's the integration of some function. I'm going to call this function f subscript x d lambda with respect to the Lebesgue measure. And for decorative purposes, I'm just going to put a dot over here, and I'm going to put a dot over here. Because you want to understand this is that because this is a probability measure, it is acting on these are Borel sets on the real line. So if you want to calculate the probability measure of a Borel set, you simply integrate this function in the Lebesgue sense over that set. And then you do something very similar with the other one. And the other one, py, would be given by integration of a different function, which we're going to simply denote as f subscript y. And just like before, this is a probability measure, so it acts on Borel sets. And the way it acts is by integrating over that Borel set. You should understand that this is actually very similar to this because this is a sum of point masses, but you could, if you want to, if it helps the analogy, you could interpret this as a of I. This is sort of like a function evaluated at every index. So it's the parallels become even closer. So this is what happens when they're absolutely continuous. And it would be convenient to introduce some letters for the sake of notation. So I'm going to write it like this. Instead of writing d lambda, this is after all a Lebesgue measure, I'm going to write this as f. I'm going to write it in like more classical notation. I do not want to use the letter x because then you can maybe confuse the variable for the random variable. So I'll write it like this, f of s ds, and this is f of t dt, and the ds and the dt at the end, these are merely symbolics. This just indicates that this is usual Lebesgue integration of a function of a single variable. I want to intentionally use two different letters for the sake of notation, just like over here I use an I and I use a J, because when you put them together, it's helpful to use different letters to tell them apart. So this is what happens when x and y are absolutely continuous. And then, so, and by the way, to remind you again, this function over here, this function is called the PDF function of the random variable x. That's what we call the PDF. It's in the case when something is absolutely continuous, there's a function that you have to integrate over to get the probability measure, and that function is what you call the PDF function. So then, when you join the random variables together into a vector, that this random vector is also absolutely continuous, and its PDF, it's going to have a two-dimensional PDF. And the distribution that you get, it's going to be given by integrating. And here you can see what was happening. Here you multiply the coefficients together. And these coefficients are sort of like functions. This is A evaluated at I. This is B evaluated at J. So this is similar. You're going to multiply these together. So it's going to be f x of s, f y of t. And then at the end, if you want to, you can write ds dt or dt ds, or you can write dA, or you can write d lambda tensor with itself, whatever notation you want to use at the end. This is just integration of a function of two variables, and you're integrating over the Borel set. In this case, this is going to be a Borel set in R2. So that's what we're saying. If you prefer, this is the same thing as saying that the Radon-Nikodym derivative of this probability measure with respect to the two-dimensional Lebesgue measure is given by the product of these two functions, of these two PDFs. So you're saying now this what you're getting over here, this is the PDF for the joint distribution. What you want to say is that this is the probability density function for the random vector that you get when you join them together. And this has to be a function of two variables because this is a random vector. This is a two-dimensional random vector. So its probability density function would be a function of two variables. And the way you find that PDF function is by just multiplying the two individual PDFs for each of the two components that make up the random vector. That's what we're saying. And as I've said, both of these are very similar to each other. Let me go ahead and prove to you part 2, and then you can prove part 1 yourself. Here's how we prove it. So this is proof of part 2. So to show, maybe I should say what the goal is. So the goal is to show that Pxy, when you integrate it over a Borel set, is given by this integration. So you want to integrate something. You want to integrate a Borel set. So you pick a Borel set, let's call it E. And it's the same thing as integrating over E of that function for all Borel sets E in the two-dimensional Borel algebra. Because now we're working in the real plane. And without loss of generality, we can assume that this Borel set has a very special form. Because the Borel algebra is generated by all of the rectangles. So it is enough to only prove it for rectangles, and then from there it will follow in general. So it is enough to assume that your Borel set has the form. Now, this notation is a little bit unfortunate because here I and j represent intervals on the real line, whereas over here I and j represent an indexing set. So I do apologize about that choice of notation, but I'm sure the reader is able to understand from context what we're referring to. So we can assume that our Borel set is a rectangle that's a product of these two intervals. So then, also, I would like to say that the product measure is uniquely determined by what it does on rectangles. That's part of the theorem. There's a unique product measure that satisfies the properties that you wanted to on the rectangle. So it's enough to just work on rectangles. So then the probability distribution of the random vector applied to that rectangle is equal to, and this is by definition, actually, sorry about that. This is by independence. Well, I guess you can say it is by definition because that's the definition of independence. But by independence, the distribution on the random vector is the product distribution of the two random variables on that rectangle. But how is the product distribution defined on a rectangle? It's the product of these two by themselves. Now, what happens over here? Well, this is because, now let me scroll up to remind you, you see, this is an absolutely continuous random variable, so its probability measure can be calculated by integrating over an interval of that function. So that's exactly what we have over here. So this is the integral over I fx of s ds, and by ds I just mean regular Lebesgue integration, and this is going to be integral over j fx of t dt, whereas on the left side, oh, sorry about that. And then in the end, we have that this is the same thing as integrating. You're probably used to writing double integral I cross j fx of s. And over here, I, of course, meant fy of t. Fy of t ds dt. But usually in mathematics, we write down a single integral, and we understand from context what we mean. So this is what you're integrating, but that's exactly what we wanted to show, right? Our goal was to show that the joint distribution applied to a Borel set is given by this integration over this Borel set. So now we're assuming the Borel set is a rectangle, and that's exactly what we're getting. What we're getting is that the joint distribution, the joint probability distribution of this rectangle in the end, when you run through the calculation, it is given by integrating over that rectangle the product of those two functions. Now, maybe you might wonder why this is true. One would justify that. So here it seems like one way to justify this is by using Fubini's theorem, as we mentioned. So it looks like we do need Fubini's theorem after all. So previously I was saying maybe we're not going to need Fubini's theorem, but it looks like it comes up. It looks like we do need Fubini's theorem. Essentially, you're integrating with respect to S. This is like iterated integration. That's what Fubini's theorem is. So you're keeping T fixed, so you can factor this out, like in front. And then you have this integral, and then this is the remaining integral. So that's what it has to do with. So there's different ways you can justify it, but that's what it is. I know over here I'm writing two integrals, but it's just notation that I'm putting one over there. So that's the way you would justify that. And now I want to do an example with you. I will provide you of an example where we have two random variables that are independent first, and then I'm going to provide you when they are not independent, so we get to see both. In this example, our sample space is going to be the unit disk. And the random experiment is we're going to throw darts blindfolded. We previously discussed a very similar example where we had a disk. In this example, however, we have a square dartboard, and we are throwing darts into that dartboard in a blindfolded way. Blindfolded simply indicates that we have no preference where the dart lands up. It's not like we're trying to aim for the center because we do not see the center. And I leave it up to you to figure out what the correct probability measure is. It's very similar to the previous example that we've done before. I'm sure you can fill in the details. I'm being a little bit sloppy over here. I'm just saying what the sample space is. For this to be a mathematically formal random experiment, we then have to then say what the Borel algebra is. Well, not the Borel algebra, but the sigma algebra is, what the probability measure is on that sigma algebra, and all of that. But I'm just saying what the sample space is, and you can probably figure out the rest. And we're going to have two random variables here. When we have a point, if we have a point, sample point, that sample point has two coordinates. Let's call those coordinates A, comma, B. That's our sample point. And we have two random variables. We're going to have X and Y. These are going to be random variables that map the sample space into the real line. And what they do is X of a point will extract the horizontal position, in other words, the X coordinate, and Y will extract out the Y coordinate, which is typically what we refer to as the vertical position of a point. Now, first of all, let us find the distributions of X and Y of these two random variables. So let's think about this. We are throwing a point randomly somewhere inside that square, and then we just project the point down, and that gives us the X coordinate. If the point is here, we just project down. So we just keep on projecting it down, and we just find the horizontal position of the point. Now, if you think about it, X produces a number. So intuitively, X produces a random number between 0 and 1, because the first coordinate is between 0 and 1. So X will produce a random number between 0 and 1 in a uniform manner. In a uniform manner simply means without any preference of where it is in the interval. So it appears that X should follow the uniform probability distribution on the interval from 0 to 1. We do not really care about the endpoints, because the probability for X to be equal to exactly 0 happens with probability 0. It's not going to really affect anything. What does this mean? So what this means is, i.e., X is an absolutely continuous random variable whose probability density function is given by, so the probability density function, let's call it fx of s. So this would be the function that's given by the following formula. It would be equal to 1 if s is between 0 and 1, and it's equal to 0 if otherwise. And the picture of this PDF will look like this, that between 0 and 1, it's just horizontal, and then over here it's 0, and over here is 0. And so it would mean that if you want to calculate the distribution, the probability distribution of x evaluated on some Borel set, so you want to determine the probability that you land there, you would simply integrate over e against this function. That's what you would do, which should make sense, because if the event is outside, you're asking what's the probability that x lands into a negative number. Well, that's impossible, because the random experiment, the random variable, will always produce a number from 0 to 1. So you can justify this more carefully, but that takes more work. I think this is fairly believable, that it will follow the uniform distribution on this interval, and that's what it would be. What about y? Well, y would actually be the same thing, because when you project the points onto the vertical side, it will also produce for a number between 0 and 1, and it does not really have favoritism of where it wants to end up. They're all equally likely. So in a similar way, y is also follows the distribution of y also is uniform on the interval from 0 to 1. And so the probability density function, I'm going to use a different letter here for convenience, will be equal to 1 if t is between 0 and 1, and 0 if otherwise. So it's going to actually be the same exact function. You might find this a little bit confusing at first, because these are two different random variables. X and y are different random variables, but they have the same distribution. So let me just say it over here. X and y are different random variables, because they're calculating different things. However, they have the same distribution. That's okay. To make it a little bit less confusing, how can they have the same distribution is, imagine we're throwing, so this is an interval from 0 to 1, and this is another interval from 0 to 1. And this is our random experiment. So we throw a point inside the square, and then we calculate the x coordinate, which would be over here, and then we calculate the y coordinate, but the y coordinate is, as you can see, somewhere near the top. So it would end up over here. And then you do a random experiment again. If you end up over here, the x coordinate would be there, and the y coordinate would actually be somewhere near there as well. And now if you imagine doing this experiment thousands and thousands of times, and you keep on filling up these points in a uniform way without any preference, because this is done in a blindfolded way, you just fill this up in this uniform kind of a way on this interval, like all over the place. And the point is, the way you fill up these dots would be different here than there. That's what it means to say that x and y are different random variables. But the distribution of the points that you're getting is going to be the same. They will all be evenly distributed throughout that entire interval. So in the end, they follow the same distribution, even though the random variables happen to be different. Okay, now we're going to, so we claim that x and y are independent random variables. Now, before we justify this mathematically, I would like you to intuitively think about why that's the case. It's always nice to develop an intuition for what we're doing. So let's say I told you that x is equal to 3/4. Can you determine what y is from there? So if x is equal to 3/4, I know that my sample point has to be somewhere along that line, because that's where x is equal to 3/4. Does that tell me where y is? No. Y could be any number between 0 and 1. It does not really give me any more information that I had before. I'm not getting anything. I cannot pinpoint further where the sample point is. I'm not getting anything extra out of that. So that's what it means to be independent. Knowledge of x does not influence what y is doing. So intuitively, x and y should be independent. Now, how do we justify this? So to justify that x comma y are independent, we first compute the probability density function of the joint random vector. So we join them together into a random vector. So this is now a mapping from the unit square into R2, because x is producing for you a random number, y is producing for you a random number, and together the pair produces for you a random point or a random vector, whatever language you prefer to use, somewhere in R2. And what is the probability density function of this? Now, the probability density function of that is going to be a function of two variables. So I'll write it like this: f subscript x comma y. This is going to denote the probability density function of this random vector. This is going to be a function of two random variables. Before I say anything, so in a similar way, the probability distribution, so the distribution of that random vector, would now be a probability measure on R2. And it would be uniform on that square. You can use open or closed interval, does not matter. It will be uniform on that square. So the difference is that x and y, these are random variables. They're giving you numbers. So that's why x and y were uniform on an interval, whereas the random vector, it is giving you a point in R2. And the number and the point that it produces, because x and y themselves always produce a number between 0 and 1. Whatever this random vector is, it's going to be a number between 0 and 1. So it will produce for you points in the unit square, and it's going to produce them for you in a uniform way, because that's exactly what it means to be blindfolded dart throwing. So that would mean that the probability density function, instead of being, you can see in this picture, it's just constant over the interval from 0 to 1. For the random vector, it's going to be constant throughout that entire unit square. So this is going to be a function of two variables, because this is a two-dimensional. This is a probability measure on a two-dimensional space. So it's going to be a function. The probability density function is a function now of two variables. And what is it going to be? It's going to be equal to 1 if s and t fall inside that square, and it's going to be 0 if otherwise. And if you want to visualize how this looks like, well, here's how you would draw it. Let's say the axis that's going towards you is the s-axis. This is the t-axis. It goes further back. And the axis that's going up, this is the f-axis. I'm not going to write f subscript that. That would make the picture too messy, but the f is just referring to this. And we're saying that over this square where s is between 0 and 1 and t is between 0 and 1, so let's go ahead and draw that square over here, that over that square, the function is constant, and it's equal to 1. And then if you move outside the square, it's just flat. And all the way over here, the function is just equal to 0 everywhere else. So it's like a suspended, it's a very similar picture. It's just like a two-dimensional version of what we have. That here, this interval is suspended, and here, instead of an interval, it's just a piece of the plane, which is just suspended 1 unit up. It's the same kind of idea. And how do we check? So to show that x and y are independent, we need to show that the distribution of the random vector is the product of the distributions of the two individual random variables. And this is equivalent, and this is why I mentioned the proposition from before. You can phrase this in the language of probability measures, but you can also rephrase it back in the language of PDFs. That was the proposition from before, because x and y happen to be absolutely continuous random variables, so they have PDF functions. And this is an absolutely continuous random vector, so it has a PDF function. So you just have to check that the probability density function of the random vector is indeed equal to the probability density function for x multiplied by the probability density function of y. And this is correct, because look at the way these are defined. This one is defined to be 1 only if s and t are both between 0 and 1, and otherwise it's equal to 0. But what about these two? Well, if you go back to what these functions are, as you can see, fy of s, it's equal to 1 if it's between 0 and 1 and 0 otherwise. So what's going to happen is when you multiply these two functions together, it's going to be 1 multiplied by 1, which will give you 1, assuming that s and t are both between 0 and 1, and otherwise it will give you 0 if you fall outside those bounds. So this condition is satisfied, which means that we have independence, that these two random variables are independent, because the joint random vector, when you put them together into a random vector, its distribution is then the product of those two distributions. And now I'm going to give you an example very similar based on this, where the random variables are not independent. It's a very similar example, but this is going to involve the circular dart. So here we're going to have, this is going to be the unit disk. And the random experiment is that this is blindfolded darts on this unit disk. And when you have a point, a sample point, so it's given by a complex number, you can then define x of that complex number to be the x coordinate. So the x coordinate, that would just be the real part of the complex number, and the y coordinate would just be the imaginary part of the complex number. So you have these two random variables. And we claim that x comma y are not independent. Now, before we justify this in a mathematical way, let's try to give an intuitive explanation to convince you why that is not the case. So let's say I was to tell you that the value, so I'm going to tell you this, a random experiment was done. I do not tell you what happened, but I go ahead and I tell you that x is equal to 0. So that would mean that on your dartboard, the point, the sample point, has to be located somewhere over there. That's where the value of x is equal to 0. So it does not really tell you what y is. Y could be any number from -1 to 1. Now let's say, so then y could be any number between -1 and 1. And if you want, you can include, I mean, it doesn't really matter. Those happen with probability 0. If I tell you instead that x is equal to, let's say, 1/2, then that would mean you're somewhere over here. So, but then look at that. Y cannot go all the way up to 1. This is sort of the maximum that you can reach. The value of y cannot actually go all the way up to 1. So by telling you that x is equal to 1/2, I'm limiting the possibilities for y. You're getting some kind of information out of that. If I was to tell you, if you want to look at it, the extreme example, if I was to tell you that x is equal to 1, then that would mean you're located right over there. And then y has to be equal to 0. There's no other way, because you have to stay within the disk. So by changing the geometry of the dartboard, these two random variables, the x and y coordinates, now are no longer independent, because by giving you a value for x, it does not matter which one. I can either use x or y. Let's say I use x. By giving you what x is equal to, I might not know exactly what y is equal to, but I'm able to gain some kind of information out of that. I'm now able to say something about y, and that should indicate why these random variables should be dependent. Now, how do you justify this? So the way you would justify this mathematically is it's a very similar procedure. So we will compute the probability density function for x. We'll compute the probability density function for y. And we're going to compute the probability density function for the random vector when you join them together. And then we're going to show that fxy would not be equal to fx of s fy of t. That's what we would show. So let's go ahead and do that. Interestingly, it's easier to start with the random vector. You would think this is harder because this is a two-dimensional random vector. This is actually easier. So here, x comma y, the random vector, just like in the previous example, this is going to be uniform on the unit disk. So this is going to, because x and y is producing for you a point somewhere in this unit disk. So the random vector, and it's being done blindfoldedly, so there's no preference where the point ends up. So it's going to be distributed in a uniform way. So when you actually write this out as a function, you would say it would be equal to some constant if s comma t is inside the unit disk. And the way you say this mathematically is you would say s squared plus t squared is less than 1. That's if you're inside the unit disk, and 0 if otherwise. If s squared plus t squared is bigger than 1, and we do not care about what happens when it's exactly equal to 1, because it's not going to really influence the probabilities. You can write it like that if you want. And then to figure out what the correct constant is, you just have to make sure that the whole thing integrates to 1. So the picture here would be that if this is the s-axis, this is the t-axis, and this is the function axis, then the picture would be it's very similar to the previous picture where you had a suspended square. This is just going to be a suspended disk, and then off is just going to be 0 everywhere else. So that's the way the probability density function would look like for this random vector. You want the volume underneath the curve to be 1. So this is a cylinder. It has a certain height. The height is c. So you have c times the base. So the area of the base would be pi radius squared, which is 1. That has to be 1. So the constant has to be 1 over pi. So the correct constant here is 1 over pi. This just ensures that the probability density function, because whatever function you write down, you have to make sure that when you integrate it over R2, it's giving you exactly 1. So that's just a condition that you need. So you have that over there. Now, so this is the probability density function for the random vector. The probability density function for these two random variables is actually a little bit trickier. So at first, you would think it's uniform, but that would be incorrect. So here's why. So we go back to this experiment again, and you can see that the real component of the complex number at the very most is +1, and at the very minimum it's -1. So that would be the real component. Now notice that it's more favorable for the real. So I'm just looking at x, right? So I'm just looking. So x of a complex number, that's the real part of the complex number. That's the way we're defining the random variable x. So we're just looking at the horizontal projections. When you have a complex number, just looking at the real part of that. You should notice that if you want the real part to be somewhere closer to 1, you have to be somewhere over here. If you want it to be closer to -1, you have to be somewhere over there. That does not take up a lot of space on the disk. But if you're closer to the middle, then you can see there's more space for it to be closer to the middle. So this would mean, based on our intuition, so I'm going to do this using our intuition, and you can justify this a little bit. You can justify this yourself afterwards. We actually did a very similar example, if you recall. We did a very interesting example. We did an example where we had the random variable where x of a sample point was norm of that sample point. It was just the distance to the center, and we figured out what the PDF was. So we used a method there. You can use a very similar method to figure this out, but I'm going to use our intuition here, and you can work out the calculus yourself. But the idea would be that the PDF function for this random variable, when you draw it in a graph, it would have to go from -1 to 1, because these regions are just impossible. It is impossible to produce it is impossible for the real part of this complex number to fall outside those bounds. That's the very most, that's the very least. So it has to be somewhere over there. And it's more favored to be in the middle than off the middle. So that would mean, and you can see it's also symmetrical. It's also symmetrical. So you would therefore guess that maybe it's like a triangle. It cannot be flat. It has to be something like that or whatever. But what kind of a curve is it? So it's not a surprise, because this is a circle, that it should be a circle. So it's going to be the equation of a circle. Well, technically, it's going to be the equation of a semicircle. And how do we find the equation of a semicircle? So it will be 1 minus s squared, square root of that, because you want the upper half of it. This is for s between -1 and 1, and it would be 0 if otherwise. And just like before, you just have to appropriately adjust it by a constant, because the area underneath the semicircle, you have to make sure that this is something that integrates to 1. The area underneath the semicircle would be, this is a semicircle, so that would be a half pi, pi over 2. So the correct constant here would be 2 over pi, like that. So that would be the PDF function for this random variable. And a very similar argument, y is essentially the same thing, it's just being projected onto the imaginary axis. It would actually be the same thing. So x and y are different random variables, but they have the same distribution. So the PDF function here would be 2 over pi square root of 1 minus t squared. And this is for t between -1 and 1. So now if you multiply them together, fx of s multiplied by fy of t, that will give you the following function. It would be 4 over pi squared. It'll be square root of 1 minus s squared, 1 minus t squared. This is if s comma t fall between, it's in this square from -1 to -1, and it would be 0 if otherwise. However, the probability density function for the random vector that we just found, that one was just 1 over pi if s squared plus t squared is less than 1, and 0 if otherwise. You can see that they're not the same, right? You can see these are not the same. First of all, this one becomes 0 outside the disk, whereas this one becomes 0 outside that square. And then the actual functions that you're using, the non-zero functions that you're using, they happen to be quite different. So this shows that this is not equal to that, right? These are not equal. These are not equal, which implies that these two random variables are therefore dependent. They are dependent. So that's what this example shows. And with these examples, hopefully that makes you appreciate a little bit more what independence is and what independence is not. So the next thing we're going to now move to is I want to discuss some properties of independent random variables. Properties of independence. And I should say some properties of independence. There's many other properties one can say, but I realized that this lecture, like all of the other lectures, is becoming a little bit too long. So it would make sense to just say the ones that are definitely going to come up, and if we need some additional properties of independence, then we will mention them in a future lecture if we need to. The one that I really want to get to is this one. Proposition: if x and y are independent random variables, then, and by the way, I want to say this again, I've said this many times before, but this is very important. Notice in the statement of this proposition, I'm not saying anything about the sample space. I'm not saying anything about the probability measure. We just understand that it's there in the background. If we need to mention it, we mention it, but often we try not to mention it. Very often, as you will see in probability theory, very frequently, you never even go back to the sample space. It's just a necessity for the development of the theory. So this is the way we'll present it. So we have two random variables, they're independent. So then, and we have this amazing, wonderful relationship that if you multiply them together and you take the expectation of their product, that would be equal to the product of their expectations. And this is, of course, assuming that these expectations exist in the first place. Of course, If the expectation does not exist, it does not have to, because expectation is basically integration. To quickly remind you, I'll write it right over here. The expectation of a random variable is you integrate the random variable. It is a function, after all, defined on the sample space, and you integrate it with respect to the probability measure. In real analysis, we write it like this, but in probability theory, we do not write integrals, we write expectations. And this proposition actually indicates what we were saying at the start of the lecture, a fundamental difference in how probability theory is different from real analysis. This is used everywhere in probability theory. Random variables make up a very important part of probability theory, especially the ones that are independent, and you have this relationship that is exploited very often in probability theory. And there is no such property for integrations. You never, I mean, if you're doing real analysis, and then in a real analysis textbook, they split a product of two functions as a product of two integrals, you would immediately be very suspicious and you would think that something is wrong. Whereas in probability theory, this is used all the time. And I would like to also remark here, note, the expectation of a sum of two random variables is always the sum of the expectations, even if x and y are dependent. Because this is just integration. The integral of a sum is the sum of the integrals. This will always work. Whereas this special property, where there is no such thing in real analysis, but it's used a lot in probability theory, does work when you're dealing with independent random variables. Again, assuming the expectations exist, otherwise this does not make sense. And this is, you can kind of have this, you can say maybe a mnemonic that independence should be paired with the word multiply. So whenever you see the word independence, you should always think of the word multiply. If two random variables are independent, then that means that the distribution of the joint random vector is the product, you multiply the two distributions of the two individual random variables. If you're doing this on the level of probability density functions, then the probability density function of the joint random vector between them is then the product. You multiply the PDFs for these two. And now you get to see it again over here, that the expectation of the product is you multiply the expectations. So this is something you want to keep in mind, that independence goes with the word multiply in probability theory. So how does one justify something like this? It would probably be proven very, very differently in a probability theory textbook. But the shortest proof that I can come up with that is somewhat convincing, hopefully you find this convincing, is to do it in the following way. So let me just recall that the expectation, so if you want to find the expectation of a random variable, that would be, by definition, that would be the integral over the sample space of x with respect to the probability measure. But you can rewrite this. You can say that's the same thing as integrating the identity function on the real line. So basically, this is the function x, or maybe I should not call it x, not to confuse it. This is like the function s, right? S maps to s. That's what we mean by the identity function. And you're integrating it. You're not going to say ds, because this is not with respect to the Lebesgue measure, but instead, you're going to integrate it with respect to the distribution of x. So you get a new probability measure on the real line, and you integrate the identity function with respect to that distribution. And this follows from something that we call change of variable. This is change of variable right over here. Okay, so we're going to see something very similar that happens when you multiply. So we have our sample space, and you can map the sample space to R2 by using the joint random vector. And then you can map R2 into the real line by using the multiplication function m, where m is the multiplication function, where it takes a point in R2 and it assigns it to R. So it takes a point in R2, let's say given by coordinates s and t, and it assigns it to the product of s and t. So if you do this composition, where you first create the random vector of x and y together, and then whatever that random point is in R2, you multiply it by m, then this composition is giving you the product of these two random variables together. So if you want to find the expectation of their product, then that would be, by definition, that would be, you would integrate over the sample space xy with respect to the probability measure. But then you can say, and this is based on the change of variable theorem, that you see you want to integrate this, but what you can also do is you can rather integrate m. So you can integrate rather this function m on R2, but you're going to integrate it with respect to the, you're going to push the probability measure on the sample space all the way over to R2, so the push forward, and you're getting what we call the distribution, the joint distribution of these two. So you're going to integrate it with respect to, the probability distribution on R2. So that's what you're going to do. And then you would recall what this is. Because x and y are independent, the probability distribution of the joint random vector is the product of the two distributions. So this would then be equal to integrate over R2 this function m, and you would write over here dpx tensor dpy. So here you're using just the definition of what it means to be independent right over there. Now, this function, when you write it in terms of variables, this is basically the function s times t. S times t. And you want to say, you do not quite want to say ds dt, because that would sort of look like integrating it in the Lebesgue sense. But you would then say, and this is Fubini's theorem, so what we can see in this lecture, I was completely wrong when I said earlier we're probably not going to use Fubini's theorem. It looks like we've been using it quite a number of times today. But this would be Fubini's theorem, that you're integrating a function of two variables with respect to a product of two measures. So you would keep one fixed and integrate the other. So symbolically, what you're saying is you're integrating over R, you're integrating S. You're not going to kind of want to write ds, but really it's with respect to the first probability measure, and then you have t with respect to the other probability measure. But S, this is really the identity function, right? That's really what we mean. This is the identity function. So it's the identity function. So hopefully that makes sense, because if you keep, so look at this, if you hold S fixed, if you set S is equal to 2, you have 2t. So if you factor out the 2, you're just left with t. That's the identity function on the real line. So it's a product of these two identity functions. But then what is this? This is going back to what we said earlier. By the change of variable theorem, we actually written it right over there. What is that? That's the expectation of x. That's the expectation of x. So this is going to be the expectation of x, and this is going to be the expectation of y. So that is what we have over here. So we see that the expectation of the product is the product of the expectation. This is the proof that I came up with that I thought is the most elegant proof, because it handles all cases all at once automatically using some of the fancy language and machinery that we've talked about. But if you want to see a different proof, you can come up with a separate proof in the special case, let us say, in the special case where x and y happen to be discrete random variables. If I think it's illuminating when I prepare the homework assignments, maybe I'll add it in there and you can try doing it. So you can kind of work it out in some special cases where you assume something about these random variables. But the nice thing about this kind of argument is that it's quite general. You're not really assuming much about these random variables at all, other than the fact that the expectation exists, which justifies these manipulations, and that the random variables happen to be independent. So that's what we have over there. So this is the important property, that the expectation of a product is the product of expectations. And from here, you have an immediate corollary. There is a corollary here. And I'm going to put this on the homework because you can prove this yourself. This is actually quite easy to prove. That if x and y are independent, then the variance of their sum is equal to the sum of their variances. And of course, just assuming that these quantities exist in the first place. Otherwise, this is not going to make sense. This also explains the reason why variance was defined the way it was. So I want to quickly recall for you that the variance of a random variable is equal to, by definition, it is the expectation. So here's what you do. You take x, and from x you subtract away its average. But then you're going to look at the average square distance, where a is the average. So that's just the expectation of x. The variance, in order to have a variance, the expectation has to exist in the first place. But that alone is not sufficient, because then you need like the square quantity, the expectation to exist for the square quantity. So under these assumptions, if these quantities exist, then you can talk about the variance. So that's the way the variance is defined. We did also say that perhaps a more natural choice of a measurement of how spread out a random variable is something called MAD, the mean absolute deviation, which would be defined as the expectation of the absolute value of x minus a without the square. By the way, you have to do it with absolute value, because if you do it without absolute value, you're going to get something very silly. You'll just have x minus a, and you'll have the expectation of x minus the expectation of a. This is just a by definition, because that's what a is, and this is the expectation of a constant, which is just a. So then you always end up with 0. That's kind of silly. You want to work with positive quantity, so that's why it's written this way. And as I told you, that MAD, even though it feels more natural to use, it does not have as nice of a properties as variance has. And you can see it right here, that by using squares, you have this very pleasant property that if you have a variance of a sum, it will become the sum of the variances. And the other thing I want to finish with, and then we'll be done. There's other things that one can talk about, but then it will just become too long of a lecture. I want to quickly finish with this. So let us define what it means for a family. So we're going to have a family of random variables. It could be, and this could be a finite, countable, or even an uncountable family, a family of random variables, to be independent. This is actually very easy to define once you understand it well for just two of them. If you're wondering, why would we ever talk about an uncountable family? Well, what happens is sometimes you have a collection of random variables which are indexed by like a real interval from 0 to 1. So for every number from 0 to 1, you have a random variable. You can think of this as the value of a stock price at every moment in time. That would be like a natural application of how that would come up. But so that's why I'm writing it in this kind of a way. So here's how you would define it. I'm going to give you the wrong definition first. So the wrong definition is, you would say that for each I and j in your indexing set, for I not equal to j. So if you have two different random variables in the collection, xi and xj are independent. And this feels like this should be the correct definition, because when we talk about a disjoint family, so let's go back. So what does it mean for a collection of events? So previously we talked about events. What does it mean for a collection of events to be a disjoint family? To be a disjoint family would mean that if I take one event and I take a different event and I intersect them, I get the empty set. That's what it means to be a disjoint family of events. So you would think that for random variables, it feels similar. It's like independence and disjointness, they're different concepts. People often confuse them. They are different concepts, but they feel similar. So you would feel, it feels like this should be the definition. But actually, you need more than that. So the correct definition is a little bit harder. So the correct definition goes like this. It says, for any choices, for any distinct choices, so you're going to pick a finite number of choices, I1, I2, up to in. you just choose different indices. So you're not going to repeat the same variable, of course. So for any distinct choices, we have that if you look at the random vector, the joint random vector for all of those random variables, and you look at the probability distribution that you get. And by the way, the probability distribution that you get, this is going to be a probability distribution on the n-dimensional Borel algebra. It should be then equal to the probability distribution that it should be equal to the product of the probability distributions on each of the individual random variables that make this up. So the point here, it is not enough. This definition includes the wrong definition, because you're basically saying you have to have independence for any two of them at a time. But the correct definition actually has to include all finite amount of them at a time. So as you can see, it's more complicated. And I think what I'll do is I'll give you an example on the homework. It's an interesting example. It's not particularly that hard, but it's an interesting example that will show you how you can have a collection. So basically, it's going to be an example that's going to go like this. You're going to have 3 random variables, and you'll be able to check that these 2 are independent, these 2 are independent, and these 2 are independent. However, when you take all 3 of them together, they're not going to be independent. So you actually have to check it at every finite level. So that's the requirement that you need. So this is the way that the definition goes. And with that, we're going to finish. And let me tell you the good news. So here's the good news. We finished with quick probability theory. So we developed probability theory in a very quick way in just several lectures, so that we know the language, we know the important ideas, we know the important propositions and theorems here, and that concludes all of the probability theory that we need. And then by next lecture, we're going to start with stochastic processes, and we're going to start with a very important stochastic process. And one can even argue that this is the only stochastic process we're going to be doing for the rest of the semester, and it's something called random walks. That's what we're going to start with next lecture. We're going to define random walks. We're going to show that they exist. We're going to discuss their properties, and then from there. So hopefully, if up to this point, maybe you did not find this the most exciting material, maybe, then when we get to random walks, you will find that stuff to be a lot more interesting, and then we will appreciate the fact that we've done this recap of probability theory.